the slide where we were looking at the first example of relating the 4 variables, namely loads, stresses, strains and deformations using the 3 sets of equations: equilibrium, constitutive and kinematics. Now this was the simplest problem that we could get to. We took a rod, applied forces F1 on either side, or equivalently you can think of fixing one end and applying the load at the other end. When you fix one end, the fixture or support will equilibrate that force with the force F1. So it's essentially drawing the free body diagram of that. So either it's a free beam, free rod where you're trying to pull it apart, or you're attaching the rod to some fixture and then trying to pull it apart. As far as the beam is concerned or rod is concerned, it's one and the same. So that's essentially what we are looking at here. This is a special case where we considered the cross section to be the same throughout. You could also have a tapered kind of a structure, which is kind of common, like what you have in helicopter rotor blades or something like that. So constant cross section, but you could also have some kind of a taper, as you have in the fixed wing. Typically you have tips. Chord is much smaller compared to the chord at the root, right? So then there are certain results that we can decipher from the final equation that we got. The final equation, remember, was combination of F1 equal to A sigma 11, sigma 11 equal to E times epsilon 11, and epsilon 11 equal to dou U1 by dou X1. We are essentially combining the equilibrium, constitutive and kinematics. Then we end up with this equation. And this is precisely what we will be doing with each and every structure. So this, if you understand this process for the rod, which is the simplest case, you can very easily correlate with what we are doing for the others. In fact, in this class itself, we will look at a torque tube, torsion, and then we will look at a bending moment problem, which is essentially beam in its usual traditional sense. So that we will see all of them will eventually come to some kind of this form, where there will be the effect on one end, which will be sitting within a derivative, and the cos will be on the left hand side. And then if we solve that differential equation for u1, applying the appropriate boundary conditions, then you are going to get the effect in terms of the cos. And the factors which are going to connect these two will essentially be what we have mentioned in terms of what these things depend upon. The constitutive law depends upon the material, the kinematics depends upon the geometry, and if so happens that loads and stresses are of different kinds, then you will get some geometric feature coming out of that as well. So, but typically for a linear problem that we typically will be looking at, you essentially have the material property and the geometric property both in the numerator here in terms of like a constant of proportionality for the strain, and that constant of proportionality will always contain a material property and a geometric property. So in this case it happens to be EA, that is the Young's modulus and the cross-sectional area. If it were a composite and you had fibers running along the length of this rod, then that E would have been EL. This is longitudinal modulus of the composite, which of course you would have found using some micromechanics law, like the simplest being the rule of mixtures that you have already applied, right? Now the important thing as far as the geometry influence on this problem is concerned is that only size matters. The shape doesn't matter. So you see, I can have any cross-sectional area A. Once I fix it, it can be this A, which is a square cross-section. I can have a circular cross-section of the same cross-sectional area. Of course, I can calculate the radius by equating for this square. If it is A squared, then the radius is R, then pi R squared should be equal to A squared. So I can calculate what radius I need so that I can keep the area constant. But it didn't matter whether I have a square, rectangular, circular, I section or anything for that matter, as long as the area is A, because that's all that matters as far as this equation is concerned. But geometry is not just mere size, it's also shape. And you will see in other problems that the shape will also matter. Even if you keep the size the same, just by changing the shape, some cross sections are better at resisting the load than the others. and you already know, for example, I section is the preferred thing for bending, and we will see why when we get to the result for bending. Similarly, for torsion, you know that circular tubes are better than solid tubes, and we will see why once again when we go there, because essentially it's not just the area that matters, but also the way that material is distributed, that also matters for other problems. But here for tension it really doesn't matter, and A is all that matters, the size is all that matters, right? So now so essentially it's a cause effect relationship, in this case the cause being F1 and the effect being U1. So it's an F1 U1 relation, which is, as I said, independent of the shape. In other words, when you're designing this structure, of course you will choose an appropriate material which has a certain Young's modulus that you desire, and of course as you keep increasing your F1, your sigma 11 will increase, and you have to make sure that the failure sigma 11 is reasonably large, so that in typical operation it doesn't fail. So these are the things that you have to account for, and you see that essentially it's the material and the amount of material that you use, which is by which we mean that, because the length might be fixed, then it's just the cross-sectional area that eventually matters. So there's no preferred shape for axial members in tension, okay? But once you reverse the load, instead of applying the loads the way I'm applying here, pulling them apart, instead I push it in, it's essentially compression. You're no longer dealing with, in a traditional sense, a rod, but a column. And when you have a column, there is a possibility of failure not only through material failure, but also buckling, and it's possible depending upon the design, the shape and the size, you can have buckling either occurring before or after the material failure. If it does occur before the material failure, then you do need to bother about the shape that you include as well, okay? So let's see what that entails. So if F1 is negative, that is essentially another way of saying you are pushing into the rod instead of pulling it apart. So that's essentially compression instead of tension, and when you have that, you end up with an elastic instability possibility and buckling. And we already looked at three types of designs, the 3S: strength, stiffness and stability, and this is where that falls into the third category, and this is very much a possibility, and of course has to be avoided, especially for primary structures other than the wing skin, which is sometimes allowed to buckle. Now, how do you go about increasing the buckling strength? You have to determine which is the mode in which it is buckling, because when I try to compress this, it can buckle by bending this way. It will of course not bend this way because its bending stiffness is very large this way. So it will not buckle this way. It will typically buckle this way rather than this way, right? And but it's also possible that this can buckle in torsion. So in other words, I am compressing it, and suddenly at some load, this will have a large twist. Instead of having a large curvature of bending, it might have suddenly a large twist. And there's no such coupling present there, but just that there is some kind of a material imperfection or geometric imperfection or some disturbance because of the environment in terms of the load, a slight change in the angle of the compressive load and stuff like this, slight small change, or any one of those can eventually lead to that, and that's very much a possibility in reality when you're applying loads in a realistic situation rather than an idealized paper or computational model. So you do need to account for that. So based on that, of course, if you know that this is going to be buckling and bending, it's called as flexural bending, and to avoid that I have to increase the bending stiffness. Just like the bending stiffness in this direction is much larger, and therefore it's not going to buckle in that direction, it's going to buckle in this direction. I want to increase the bending stiffness in this direction as well. Or if I find out that this is going to buckle in torsion, I have to increase its torsional stiffness. So even though the dominant load might be just the axial load, just because it's a compressive load, I might have to take into consideration torsion and or bending as well, okay? So, and another way of increasing the buckling strength is by, for the stringer, is to bring in more transverse webs. In other words, the pitch, that is the distance between two adjacent transverse ribs, is smaller, so that now you have a shorter column, and shorter columns will buckle much later, and therefore you're delaying the buckling. So that's essentially what you could do as well. So there are three ways in which this is done. The first one is As I said, the transverse supports, ribs in the case of the wings, frames or bulkheads in the case of the fuselage. They essentially, you bring in a more number of them so that they are closer to each other rather than farther apart. And when that happens, it will shorten the length of the buckle more, right? Next, because when it buckles, it's going to either bend or twist. You can increase the bending stiffness and or torsional stiffness accordingly. To increase that, you would be, by increasing that, you would be avoiding both flexural buckling and or torsional buckling, and for which shape does matter. So that's the reason why even when you're designing purely for axial load, and you know that only A is coming into picture, whether it is tension or compression, this is the equation that will hold, but this will hold only until failure, either material failure or geometric failure, by which we mean buckling or any other instability. So either case, it's very clear that you do need to take into account the shape as well, even though shape doesn't enter this particular equation, which is valid only for the healthy structure, which has neither buckled nor failed in the sense of an ultimate material failure. So the cross-sectional shape preference exists for compressive axial members, but not for tensile axial members. So are there any questions on this particular slide? Because if you understand this, it will be very easy for you to understand a little more complicated problems that we will visit in the next two slides, because the process will be exactly similar and parallel, and you will have the same set of 4 variables, the same set of 3 equations in terms of the quality. It's just that the variables themselves will take different names and the actual equations will be slightly different, but the connectivity once again is to substitute one equation into the other, essentially combining all 3 equations into a single equation, then see the cause-effect relationship being dependent on both a material property and a geometric property. So are there any questions on this? Okay, so let's move on to the second example. So here we have a torsional member. So let me try to sketch that. Typically, most torsional members will be thin-walled, because that is the case which offers you maximum torsional stiffness. We will see soon why that is the case. Once again, as always, we introduce a coordinate system where we introduce x1 along the length. So whenever we have large, long structures which are slender in nature, so you typically introduce a coordinate system x1 so that you have consistency in all of your equations. And when you take a cross section of this, unlike in the previous case where you could look at any arbitrary cross sectional shape because shape didn't matter, only size mattered, here we are talking about in the cross section, essentially it looks like this. It's a thin walled tube such that the thickness T is small compared to the radius R of this tube, right? So now the load that I am going to apply over here is a torque. So I can, for example, fix this end, which I could have done in the previous case as well. So instead I am going to, instead of the axial load force, I am going to apply a torque. So a torque is typically represented by a double arrowhead, okay, in the same direction. So when we show like this, it essentially means the torque. And so all moments will be represented by M, whether it's a bending moment or a torque, and or you can call it T sometimes. So, but if you have 3 components, M1, which is along x1, parallel to x1, that is essentially your twist. And what this double arrowhead means is that you use your right hand rule, you point your thumb along the double arrowhead, and then you see which direction the moment is. So from this end, I see that it's anti-clockwise. On the other hand, if I had applied the arrows pointing towards, both the arrows pointing towards the left, then I would have had a clockwise moment, and that would be negative. Okay, so that is the torque. So in this particular thing, I'm calling that torque as T. So M1 equal to some value T, which is a specified, let's say, a numerical value, and like all other moments, it will have the unit of Newton meter in SI. So because Newton is the force and meter is the distance, so essentially that's what you end up with, right? So now if you draw the free body diagram of this tube, it's very clear that the support here has to offer a torque in the opposite direction. In other words, the double arrowhead going in towards the left rather than towards the right, and essentially these two will be balancing each other out. Or in other words, I'm twisting this way, here I'm twisting it in the opposite way, or if I have clamped it somewhere to the wall, I am applying only a torque here, but that wall is applying the torque over here, or whatever the fixture is attached to it is applying the torque. So so in this case, what is the load that we have? Because we want to go in the same format, that is we want and some examples of this application, of course, shafts which are like drive shafts from the motor or the engine to the place where you want it to eventually have the implication, like for example in the case of an automobile, it could be from the automobile's engine all the way to the axle of the wheels. So similar to that, so you typically have shafts. The other case is of course the wing box itself, which involves if you look at a typical airfoil cross section, you typically have a spar at the top, at the closer to the leading edge, and as another spar which is close to the trailing edge. And if you look at the web, the front web, the rear web, by which we mean these vertical structures of course, and the top skin and the bottom skin, these four when taken together form a closed loop, and that's what we call as a wing box. Okay, so these four, number 1, 2, 3 and 4, all put together constitute what is known as a wing box. Okay, and typically for larger aircraft you might have more than 2 spars, and therefore you have essentially more than one wing box, or you can think of it as a single box which is having multiple closed loops in it. We will look at both those examples as we go forward, right? And now we come back to the simpler example that we have here of a circular cross section where the radius is a constant, the thickness around the radius is a constant, even though I have drawn it differently. So what we are talking about as far as the load is essentially your torque. So T is the torque that you are applying. What is the stress which is caused due to the torque? In the previous example we applied an axial load, so we know that was an axial stress. Now we are applying a torque. The way the structure resists that is not through a normal stress anymore, but a shear stress. So we are seeing the first example of an actual practical application of the shear stress in this course, which is which we call as tau. And if you want to keep it more accurate in terms of the notations, the three-dimensional notations, here it's in polar coordinates that we will use, so, or cylindrical coordinates in the 3D sense. So it will be essentially tau 1 theta, because 1 is the direction, remember, on the phase of which it is acting. So essentially any cross section that I cut, it is going to be having a normal which is parallel to the x1 direction, or what we call as the b1 hat unit vector, and therefore the first subscript for your stress which is going to act on this, which will essentially be something like this, right? So a shear stress which is acting all through a constant value, which is essentially resisting your torque. Okay, so this shear stress multiplied by the area on which it is acting will give you the force, multiplied by the radius will give you the torque, that is essentially with which the tube is resisting the torque that you apply. So these two torques will be equal and opposite to each other. Okay, so the cos is the torque, that M1 or T that you are applying, that is the load. And now you are trying to see what is the final result of that. Of course, in terms of the effect will be a twist. In the other case we applied an axial load, the final effect was that it increased in length. Here you're applying a torque. So compared to the end which is fixed, the other end is going to have a twist. It is going to change its angle by a certain amount. It's going to rotate by a certain amount. If we call that angle as phi1, why 1 is because that rotation is perpendicular to the x1 direction. So we can in general have 3 rotations, phi1, phi2 and phi3. And phi2 and phi3 we will see when we get to bending. Phi1 is the only thing which results in torsion, right? So m1 is the cause and phi1 is the effect due to that. So now we want to relate those two. As always, it's difficult to relate them directly. So we take this intermediate process of introducing the stresses and strains in between, and then we try to connect them by using the equilibrium, constitutive and the kinematic equations. So what are they in this particular case? Let's look at that. So now as far as the the derivations we will do a little later in terms of why this equilibrium equation is like this. So take it from me for now that this is what it is. Within a couple of classes you'll be familiar with how exactly this happens. But the shear stress is related to m1 through an equilibrium equation. But once again, like in the previous example, we are not relating apples to apples but apples to oranges. Essentially the load is a moment which is having the unit Newton meter. The stress is in Newton per meter squared. So obviously there's a difference of meter cube between them. So obviously that has to come through some factor, and that factor of meter cube is J by R, where J is a new quantity that we are introducing, pure property of the geometry. Once you're given the geometry, you can get J. In the special case where it is either a circular cross section like this which is hollow, or even if the circular cross section was full, then in that case alone your J is equal to IP, only for circular cross sections. And that IP is the polar moment of inertia that you might be familiar with from other classes. So that polar moment of inertia is what this is called as torsion constant, this J, that is a pure geometric property which is a property of the shape and the size. Unlike A, the cross-sectional area which we got in the previous example, which depended only on the cross-sectional size rather than the shape, actual specific shape, here it does depend on the shape as well. And for a particular kind of shape, namely circular, both hollow as well as solid, you can very simply take J as IP. But for all other cross sections, it's a little more involved and little more complicated how you go about doing that. We will see as we go forward in the course. But I would also urge you to do a parallel study of any of the books to look at how these are calculated, and that will be part of one of your homeworks. And if you find any difficulty, we will see when you present, and I will try to bring in certain insights at that point in time, because it's also important for me to see when we have not introduced a concept how you are thinking about that concept, and then once we introduce the concept how things change. So that's the idea behind this particular homework that you will have, which is listed at the bottom of this slide, right? So now we have these two quantities, the ends, that is essentially you have the load, which is your M1, which is the cos, and then you have the deformation, which is your Phi1, which is essentially your effect. But as always, it's difficult to directly connect them. So we introduce intermediate quantities, which are the torsional shear stresses, and that torsional shear stress will be 1 theta, because the notation is, as I said, 1 is to refer to the cross section on which the stress is acting, and the direction in which it is acting, which we saw over here. It's acting in the circumferential direction, and if it's acting in the circumferential direction, it has to be, the second subscript of tau has to be theta. The first subscript is from the cross section per normal, that is 1, and the second is from the direction in which the stress itself is acting, which is essentially your theta direction, right? So now that is your tau 1 theta, and if that is tau 1 theta, then now you want to relate tau 1 theta to m1. So this is one thing which you can't see right away over here, but it's something very simple. We will see very soon. When we do that, we will see that the relationship between tau and t is through the quantity which is cubic in the length, and that is j by r factor, and that is what is multiplying over here, purely a property of the geometry. And this small r that we are talking about is the actual radius of a material point, not the overall radius of the entire component, so that you are essentially looking at going towards that, because the tau can in general change. So especially if it's a thick walled tube, then you will see closer to the center you have a little smaller shear stresses, and as you go to the outer boundary you have a larger stress, but in a very thin section you may not notice that larger difference between what is the magnitude here and what is the magnitude there. But to keep things rigorous, your small r is varying from the inner radius capital R I subscript I to the outer radius capital R subscript O, standing for outer, right? So this is what we have, and once those two are related, we next need to relate the stress to the strain. Both are shear in this case, shear stress and shear strain, and we already said it is tau 1 theta. So similarly your shear strain will also be gamma 1 theta, which is of course small gamma that we use over here, but to be consistent with our notation, it's essentially your capital gamma 1 theta over here, right? So, and this is like in the previous example where we just used E without a subscript, which means that we were dealing with isotropic materials, which is what mostly we will deal with in the rest of the course. Here also we are using G, the shear modulus, without subscripts, saying that it's the same in all directions, and therefore we can use a G over there. So this is very similar to your Hooke's law, just that the stress and the strain are no longer normal but shear, and the modulus is no longer Young's modulus but a shear modulus. So that's the only difference that you have. Next, and some of these things will become very clear when you work out that problem of proving G equal to E by 2 into 1 plus nu, or equivalently for a composite C44 equal to C22 minus C23 by 2. So there you will see this is the primary quantity which comes into picture, and that it plays an important role. So now the shear strain is also gamma 1 theta, just like the shear stress, it's 1 theta component, and that in turn purely through geometry we can show that the shear strain and the twist angle are related to each other, because shear strain is defined as a change in what is originally 90 degrees, how much it changes by, and then you can show that. We will do all of these things, don't worry. So here I'm just presenting intermediate results so that you can see the connectivity. Later on we will revisit each one of these problems in more detail and do each of these derivations fully, right? So now your gamma is equal to, therefore, the radius, the same r that we had in that expression over here, tau is equal to TR by J, same r is over here as well. So in other words, the shear strain is proportional to the radius. The farther away you are from the center, the more is going to be the shear strain. And the other factor is of course the twist per unit length. So that is essentially a derivative of the twist angle with respect to x1. Like in the previous case, we had dou u1 by dou x1, which is essentially how u1 changes with respect to x1. In the simplest case, of course, u1 is linear in x1 and dou u1 by dou x1 is a constant, but in general it can be any nonlinear function of x1. So dou phi1 by dou x1 is the right way to write this, because that way you are taking into consideration all the possibilities, okay? So, so now we have all the three equations, equilibrium, constitutive and kinematics. All that we need to do is substitute one into the other, and when we do that we eliminate the shear strain and the shear stress, which anyway were intermediate quantities we introduced just to simplify the steps. So make it small, shorter steps to reach the final goal of the deformation from the loads. So therefore we eliminate the strain and the stress using these three equations, and we end up with this final equation, which is torque is equal to Gj times dou phi1 by dou x1. If you see, exactly similar to what we had earlier. Instead of T, we had F1 earlier. Instead of G, we had E. Instead of J, we had A. And instead of V1, we had U1. Okay. So the role play has changed, but the form of the equation remains one and the same. In other words, the torque and the twist are related to each other. In fact, it's the torque and the twist rate, because it's how twist is changing with respect to x1, which are proportional to each other. And that proportionality constant, as before, involves a material property, involves a geometric property. There it was EA, here it is GJ. So that's why EA is called as the extensional stiffness, GJ is called as the torsional stiffness. So the extensional stiffness is Young's modulus times the cross-sectional area. The torsional stiffness is the shear modulus times the torsion constant. In this specific example of circular cross-section, solid or hollow, you can take J as IP, but many students make this mistake of taking J as IP for all problems, even when the cross-section is not circular. Beware of that. Okay. So GJ is what you have, and the J is of course the torsional constant. And here now we see that J is something that is going to depend on where the material is located. For this simple case where J is equal to IP, you can actually calculate the polar moment of inertia for circular cross sections and thin walled circular cross section over there. So here IP will be just this, you can look up in any textbook appendix on dynamics and or statics. You will find these listed, but in dynamics it will factor in a mass also into picture. Here we don't have the mass, it's only purely in terms of the distances that we define this moment of inertia, right? So your IP, and this is the one that we will use for the rest of the course, so be familiar with that. So that's just going to be given by pi by 2 times the difference of the fourth powers of the outer and inner radii that you have. And once you do that, you can factor this power 4 minus power 4 can be written as R naught squared the whole squared minus Ri squared the whole squared. So you can write it as their sum and their difference, and then once again R naught squared minus Ri squared can be once again factored as a sum and the difference. Once we do that, we can explicitly bring the thickness into picture, which is the reason why we are doing this. Once we get that the difference between R naught and Ri, the outer and the inner radius, is essentially your thickness that of the thin walled tube or shaft, and therefore we can replace that, and approximately we can take R naught plus Ri as the average radius, and this as the twice the average radius squared, etc. Once we do that, for when t is very small compared to R bar, which is the average radius, which either you can take as the inner or outer radius because they are all approximately equal to each other. So then you get 2 pi t times R bar cube. Okay, that is the polar moment of inertia. In this case happens to be the torsional constant as well. So we can substitute that, and once we substitute that, and we know that the area on the other hand, which was what we needed for the previous example, that for this case will just be given by pi R bar squared, and this is not the area of cross section. This is the area which is enclosed by the mid surface of that thin walled tube, right? So that area is pi R bar squared. It's not entirely occupied by material. Remember, very small part of it is occupied by the material. It's the overall area that is enclosed. So it's the entire area of this circle. If you're drawing a circle in between these two outer and inner circles, so the area enclosed by that circle is what we are looking at. Similarly, for the wing box, it would be the area in between these four plates or shells that we have. That entire area that we are talking about, this whole area is what we are talking about over there. So in terms of that, if you look at, I can substitute for R bar in terms of A bar as R bar equal to A bar divided by pi square root of the whole thing. Once I do that, we can very easily see that this J is proportional to A bar power 3 by 2. The torsion constant J is proportional to A bar power 3 by 2. Since J is proportional to A bar 3 by 2, power 3 by 2, when we multiply by G, which is purely a material constant, it still remains proportional to A bar 3 by 2. So therefore your torsional stiffness is therefore dependent not just on A bar like what we had in the previous case EA. Here you have it as A bar power 3 by 2, and this A bar is different from the A over there, that was the actual cross-sectional area, which if in the previous example I had used the same tube to pull it apart, then it would have just been 2 pi r bar times the thickness. That is all that the area was over there. That is not the case here. It is entire pi r bar squared, which is much larger, right? So that's what your Gj is proportional to, a bar power 3 by 2, right? So as I said, this is valid only for circular cross sections. When you go for other cross sections, there are other ways of determining J, which is what you will look into references in order to find out how it is done for another simple cross section, which is a rectangular cross section instead of a circular cross section, and then we will compare these two problems, right? So now what does this essentially say? What is important is not the actual cross-sectional area, but how much of area is enclosed by that mid-surface of that tube or wing box, right? So if I push the material out, rather than having a solid cylinder of the same cross-sectional area, which means the same weight for the same length, now if I try to push that material apart, make it a much thicker tube, that is larger diameter tube, but you are having the same amount of material, that is the mass is the same, the volume is the same occupied by the material, but the area enclosed within it is much larger. When I do that, I will be increasing J and therefore increasing Gj, which means that the resistance to torsion is going to increase, because the twist rate, you can take Gj to the denominator on the other side, you see it is T divided by Gj. So larger the Gj, for the same torque, you are going to have a lesser amount of the twist rate, and that's essentially what this is going to help. So in terms of the design, when you are looking at it, the one way is to change the material to a larger G material to have lesser twists. The other way is to have shapes where J can be maximized and therefore you can still have larger Gj. So both from a material and a geometric point of view, we can attack this problem to reduce the amount of twist for the same given torque, for the same length of the material for the tube, and the same material being used for that. You can try to play around with J in order to do that, right? So the net takeaway from this is that material farther from the center, and center again we are using in a very loose sense, like in the previous example I said we have to define something called the tension center. Here we have to define something called the center of twist, and once we define the center of twist, we can see the material that is farther away from the center makes the difference, and for the simple case of circular cross section, it's same as the center of the circle, which is a cross sectional shape, and therefore they are one and the same, and therefore the more you move it out, the better. Similarly here also in the wing box, the more you have moved it out, in other words you are spreading out the spars farther from each other, or you are having a thicker airfoil for example, then you are essentially enclosing a larger amount of area. Though exact same expressions will not be valid, still qualitatively it would mean that once you increase your A bar, the area enclosed, you will see that always you are going to get a larger J and therefore a larger Gj, and therefore you are going to have better performance in torsion, right? So material farther from the center takes more load and hence is better utilized. In other words, if you are putting more material close to the center, then you are actually wasting the material, because that is anyway not going to offer any resistance in stress, and when it's not offering any resistance in stress, it's like a dead weight, and weight is a huge penalty in aerospace structures. So by taking the dead weight, you are actually making a huge crime, committing a huge crime, because you are essentially wasting the material and also making the aircraft performance overall much poorer than what it could otherwise be with an appropriate location for your material, right? The other thing is for this specific case, we can see that the thin walled larger diameter tubes are much better than thick walled smaller diameter hollow tubes, or for that matter the worst case is solid shaft, because you will have material close or even at the center itself which is not offering any resistance whatsoever or very low resistance, and therefore is completely wasted and therefore you will see it's really a lose-lose kind of a game. Okay, so of course we are talking of the same material for both the solid and the hollow tube, and to just to give you a feel for the numbers, for example, if you take a 1 millimeter thick 50 mm diameter shaft, and you take on the other hand 20 mm diameter solid shaft, both of the same length, made out of the same material, you can check the calculations and see they weigh the same. In other words, they are same amount of material. But if you look at the GJ values for both, it's almost 50 times. So in other words, just by spreading out the material farther from the center towards the edges and making it a tube instead of a rod, you are essentially increasing GJ by as much as 50 times. No change in weight, no change in material, just by reshaping it, you are increasing the torsional stiffness by 50 times. And that means for the same torque, you will get 50 times lower twist rates, which means it's a much better performing structure. So this is what you need to remember. Though we have discussed this for the simple case of a circular tube, many of the qualitative takeaways will still hold for the wing box, which will be of primary importance when you're talking about aerospace applications. Okay, so the homework therefore based on this is to compare the GJ of the thin-walled rectangular box beam with a GJ of a solid rectangular box beam. What we have done in the last line of this slide is to do that for circular cross sections where J is equal to IP, much simpler. But here you have to first find out how J is determined for rectangular cross sections, for solid rectangular cross sections and for thin-walled rectangular cross sections, and then you have to compare the two. Once again, the conditions remain the same. What are the conditions? I want to keep the same mass, I want to keep the same length, so I want to keep the same material, which means the same density, and which is why the same mass as well. But then you are trying to change the overall shape by moving the walls farther apart. Now, as far as the rectangular box is concerned, it will also depend on the aspect ratio, which is what is the ratio of the breadth by the height of the overall box. So now that ratio is going to be altering this ratio. Instead of 50, what you get is going to be a function of that. Then I want you to also see, as you increase or decrease that B by A, how does it change your overall GJ. So just to sketch what I am asking for, this is what we have. One case you have a solid cross section. Now the same material I am spreading out into a much larger box over here, which is having the same cross sectional area because already it has the same length. So only by having the same cross sectional area it can have the same mass. So I want to get to, oops. Oh, okay. Thank you. Yeah. So you see that you have this kind of a cross section. So where there is material only on the edges of this section, you should find out how to determine the GJ for such a, in particular J, because G remains the same, which is the material property. How to find J, which is not equal to IP, and here also how to find J for this. Also you want to determine how, and once you do that in terms of course, the A, which is the length, and B, which is the height of this particular thing. And in this case you have not only a different dimension A and B, but also you also have the thickness that you're dealing with this thickness being much smaller compared to let's say A star and B star, which is what this will be, right? This special case of course will be a square where A star equal to B star, and that will be much simpler to compare as well. So first search books and or internet to find out how to get J for rectangular cross sections, solid and hollow, and then use this comparison, use the same amount of material in both. Length is already same, which means cross-sectional area is what matters. But then you will see once again, it's not the cross-sectional area A which matters, but A bar, which is the amount of area which is enclosed by the mid surface of this. That's the hollow portion that is there essentially. That's what is going to make a huge difference in terms of increasing your J, and therefore you can compare the ratio of these two, just like we did in this last line, to compare for a solid circular and solid circular on the right hand side and the thin walled on the left hand side, to show a factor of 50. Are there any questions on this example? Okay, so let's move on to the last example that we have of the simpler problems, and this is bending, and in this case also we will have the exact same process, and an example of an actual application is this spar that you see over here. Now we are looking at not just the webs of at the front and the back along with the skins, but just this portion which involves the flanges as well. So the top flange and the bottom flange of the front spar along with the front web, together they constitute a spar, and so structures like that typically much better at bending, because like an I section which increases a quantity called the moment of inertia about the neutral axis, which is what you will see at the end result over here. Instead of EA or GJ, we are going to end up with an EI22, and therefore the material property is same as for the first example, that is for axial load, but as far as the geometric property is concerned, there it was cross-sectional area, here it's the moment of inertia about the neutral axis, and that is what is going to determine it. And for the neutral, for the moment of inertia, I sections do really well, and which is why most of your spars are I sections. Okay, so now let's see how we go about doing this. And this is broken into two parts, because the bending can either be a bending by using a pure moment, or it can be because of a load that I'm applying. So in other words, if this is the beam, so and one end I'm clamping, the other end I can apply a bending moment. Earlier, remember in the previous problem, we are applying a torque, which is also a moment. But now we are changing the direction of the moment. It's not along x1, but it's either along x2 or along x3. Okay, so when you have that, you essentially have a bending moment that is caused. So now I can either apply such a moment at the tip to get a bending moment throughout, or I can just apply a transverse load. So in other words, I apply a load which is perpendicular to the beam's length, and when I apply that load, that is going to also cause a similar effect of bending, but it's also going to cause a transverse shearing stress. So we will take both those examples. The first example, 3A, will be about the pure moment, and 3B will be about a moment which is having along with the moment also a shear force, which is of course in the transverse direction, which is why it's causing a shear stress in the cross section, right? So now let's see what happens. So instead of an I section, we'll take a simpler model of just a rectangular strip, and rectangular strip has a length L, a breadth B, and a height H. And as always, we introduce along the longer dimension x1, and the next larger dimension x2, and the third, which is the smallest dimension, we introduce x3. This is the coordinate system that we have. Once we have this coordinate system, we are applying a particular moment, and once again we use a double-headed arrow to showcase that it is a moment, and therefore this is a moment like this, which is essentially bending it such that the top fibers are all under tension and the bottom fibers are all under compression. Okay, I'm saying fibers even though it might not be a fiber composite, because essentially you're thinking of the material to be made out of, let's say, long fibers. Essentially you're seeing that that's essentially what's happening to individual fibers. So it's very clear that the top is, the way I have applied this bending moment, it's very clear that the bottom is going to be under compression, the top is going to be under tension. So that is that means that the top layer is going to be increasing in length, and the bottom layer is going to be decreasing in length, which means that in between them there has to be one layer which is not at all changing in length. Okay, so because one is increasing, the other is decreasing, and it's changing through the thickness of this. At some x3 value, you will find a layer which is not at all changing in its dimension, and that's what we call as the neutral axis when you're looking at it at the cross section. So similarly, you can have the entire thing, if you look at it, it's a neutral plane, and you can have two neutral planes intersecting when you're talking of two different bendings. What is shown here is M2. Similarly, you could have an M3 which is parallel to X3. Here it was parallel to X2, which is why we called it M2, whereas the torque in the previous example was parallel to X1, that's why we called it M1. And so the two bendings will always be in the cross-sectional coordinates. X2 and X3 are the cross-sectional coordinates. M2 and M3 will be the bending. M1, the other one, which is along the length, will always be a torque. Keep that in mind. Okay. So now you have this possibility of either M2 or M3 or both happening simultaneously. So each of them will introduce a neutral axis, and then those two neutral axes will intersect, and that will form a line. So that is essentially the overall neutral axis for the entire structure. So you can determine, because in general you will have both kinds of loads, and especially in the example that we are looking at from an aerospace point of view, the wing box, you know that there's going to be a lift distribution which is going to cause your if you call this, let me put the coordinate system over here. So X2 and X3, of course, as always, the coming out of the board is your length X1. So once you have something like that, you have a bending moment X2, which is going to be M2, that is caused primarily by the lift distribution. It's going to be fairly large because the lift distribution, the lift is much larger compared to the drag. Now there is also a drag force which is pushing the wing backwards. So essentially that is going to cause a bending moment about your X3. Okay, so that is going to be your M3. So in other words, both M2 and M3 are simultaneously present. Usually your M3 values will be much smaller compared to M2, and also it's much thinner in the M3 direction compared to M2 direction, because M3 direction is phasing the total thickness is essentially the thickness of the airfoil, whereas M2 is phasing a thickness which is essentially the chord of the airfoil, and therefore you're looking at a much better response that you have as far as M3 is concerned. So that's not going to be so critical. M3 is not going to be so critical. One, because the drag is small compared to the lift. Two, because there's also going to be a thrust which is going to be counteracting if the engines are mounted on the wing. That's going to be counteracting the drag. So therefore you're going to further reduce the moment. Then the resistance offered to it is much more because there's a larger thickness which is along the chord rather than the thickness of the airfoil itself. So all these will make M3 not such a difficult thing to deal with, but nonetheless, to be accurate, you need to consider both M2 and M3, and you typically will end up with a neutral plane or neutral axis which is somewhere like this. So not horizontal, but making some angle. So taking both of these into account, where you would neither have tension nor compression, and so no change in length that will happen for the material points on that line, but every other material point would move out or move into this plane in order to make this whole cross section to rotate in some direction, right? So now let's once again do this same problem in the same process. 4 variables, loads and displacement being what, your deformation being what are the cause and the effect, but intermediate we introduce the stresses and the strains, and instead of direct connection between load and deformation, we go step by step. First from the load to the stress, that is called the equilibrium equation, that has to relate your stress, which is going to be sigma 1,1. So once again note that just like in the first example of the tension on the rod, you are going to have a stress which is 1,1 sigma 1,1, the normal stress in the 1,1 direction. Why is it so? Because when you're applying the axial load, it's very easy to see that the axial load and the stress are in the same direction. But what about bending? The bending can be thought of as made out of two forces, one which is pulling on the top, the other which is pushing on the bottom, and therefore you essentially have a bending which is happening because of two axial loads, one positive, one negative, and both are going to result in axial stresses only. At the neutral plane, the axial stress will be 0, axial strain will be 0, and which is why there is no change in length. Now, the stress is sigma 11. The moment that you are applying is M2. Once again, these are of different dimensions. Stress is having a unit of Newton per meter squared. Moment is having the unit of Newton meter. Just like in the previous example, there is a difference of meter cube, and therefore that factor is I22 by x3. So that is the factor. This has the unit of meter per 4. This has the unit of meter, and so essentially that brings these two quantities together. As I said, equilibrium equations in their original sense will not depend on the geometry, but here they seem to apparently depend on the geometry purely because we are comparing apples to oranges. One case you have a moment, the other case we have a stress, and therefore we have this particular equation. But essentially it's a relationship between sigma 11 and M2, with the constant of proportionality being x3 by I22, but actually not a constant because x3 is varying from minus h by 2 to plus h by 2, the thickness, and therefore it's going to have a slight variation based on that. And it's because it's going from minus h by 2 to plus h by 2, it has negative values as well as positive values, whereas these two, the way they are shown, I22 is always positive anyway, and M22, the way it is shown, it's along the positive x2 direction, and therefore that is positive. So you see that x3 can have positive or negative values, therefore sigma 11 can have positive or negative values, which essentially means tension and compression on either side of the neutral axis. Okay, so the four variables are M2, sigma 11, correspondingly your gamma 11, and your, very interestingly, though in the case of the axial load, it was very easy to see that the end effect of an axial stress is an axial strain and an axial displacement. But here, even though you are applying a bending which is about M2, the primary effect of that is going to make this curved, and therefore even though there might be a small change in length of the top and the bottom most layers, the much larger effect is in terms of getting a curvature. And therefore the deformation or displacement, which is of much larger consequence, is going to be your U3. So in other words, you are applying load is M2, your stress and strain are 1, and your displacement is 3. Okay, so all three directions are involved. That's why bending is such a complicated thing, especially for beginners. But once we get a feel for what is actually happening and we put it in this overall perspective, then you see that things very clearly fall into space. And why bending displacement is important is because the end result of bending this is going to, instead of a straight line, it's going to take a U shape now. Now that shape essentially means that material points have gone down, and that is your U3. That's the vertical direction is the x3 direction that we introduced in the coordinate system. So it's the same direction that we are having the largest displacement. So that's what we are primarily bothered about. There can be coupling and a few other displacements can be there, but they are not going to consume as much energy or store as much energy as your U3 displacement, and that's why this is the direct effect that we are bothered about. Again, the strain being epsilon 11, the relation, you know that epsilon 11 is defined as dou u1 by dou x1. But dou u1 by dou x1 is something that is valid in your three-dimensional model, but once you bring in this beam displacement of a u3, you will see that it's u3 which is going to affect it, and the actual reason why this is so we will very shortly see. When we look at what actually happens to the bending deformation, it's very easy to see. It's essentially the curvature times the distance from the neutral axis, and that's the product that we are having here. So right now you just take it from me for granted that this is what is the strain displacement relationship. We will revisit it, do a very short small derivation to show indeed this is the case as we go forward. Now it's all about combining these. The middle equation, of course, very similar to what you had in the axial rod, because axial stress, axial strain, the Hooke's law applies, and Young's modulus, and because we are dealing only with isotropic materials, you do not have any sigma 2 and sigma 3. If you had an isotropic material, you will have to have those complications as well. Here we want to keep things as simple as we can, right? Now all that we do is substitute the kinematics into the constitutive law into the equilibrium equations. So essentially we are combining all these three and we are eliminating sigma 11 and we are eliminating epsilon 11 or gamma 11. And once we do that, we have a relationship between M2, which is the cos, and U3, which is the effect. Okay, and the relationship between them now involves not a first derivative like it did in the previous two examples. Remember, in the first example we had a dou u1 by dou x1 for axial load. For the second example for torsion we had dou phi1 by dou x1. Both were first derivatives. Now for the first time we are seeing a second derivative, which is also another reason why bending problems are a little more complicated compared to torsion problems and axial tension or compression problems. Unless of course the compression reaches the case of of buckling, where bending will also become a part of the axial axial load problem. So now once again the coefficient which is connecting these two is a factor EI constant, which involves contributions both from a material property and a geometric property. The material property which contributes here, unlike the previous case which was G, is like the first case, which is E. As far as the third is concerned, the geometric property is very different in all three cases. First case it was A, the cross-sectional area, so shape didn't matter. Second case it was J, shape mattered a lot apart from size, and size matters in all three cases. So here also the shape matters, which is why an I section is very good here. In the previous case a thin wall tube was very good, or a box beam was very good. Here you see that factor, the geometric factor, is a moment of inertia about the two direction, and this should not be confused with the dynamics moment of inertia, which involved a mass as well. This is without the mass, it's purely a geometric property. That is what I22 is. So if you want to reduce the curvatures, reduce the deflection of the beam, the dangerously looking tip deflections that you have seen in wings, if you want to reduce them, there are two ways of doing it. Use a material which has a larger E, or use a geometry which has a larger I22. Either way you can do that, or you can use some combination of both in order to achieve that. Now what is this I22? That is the moment of inertia about the x2 axis, and therefore it's just given by how far we are from the x2 axis in the cross section. How far you are from the x2 axis in the cross section is determined by the x3 value, because this is the x2 cross axis, and how far you are from the x2 axis is determined by your x3 value. So essentially it's your integral of x3 squared. It's of course an area integral which will involve a double integral eventually, but it's x3 squared dA, and dA is the area element in the cross section, has to be integrated over the entire cross section. Now this can also take care of situations where you have different materials. We can factor in that material property into that, and you can integrate E times x3 squared dA. It's essentially a weighted kind of moment, just like in the case of what you did with dynamics, where you put the mass inside by introducing the density of the material. Here you can do something similar to that as well, right? Yeah. Now if M3 is also applied, because in our example we saw that lift distribution is giving you one moment and drag distribution is giving you another moment. So M2 and M3 are present simultaneously. Whatever we have shown here is valid when only M2 is present, there is no M3. But if M3 were also present, it's quite straightforward thing. We will once again have E. Instead of I22 we'll have I33, and instead of U3 we'll have U2. So it's just, and of course we have to take care of the appropriate signs based on the convention for the positive stresses, etc. Once we do that, positive displacement, positive stresses, and positive curvature, therefore all of that will take into account, and therefore we can relate M2 and M3 which are both simultaneously present, and this expression will no longer be valid. It will have additional term which is contribution of curvature from the other direction. So therefore U3 double prime or U2 double prime, which is nothing but dou squared by dou x1 squared, I am writing as double prime. So that both U3 double prime and U2 double prime will be a function of M2. Similarly, both of them will be a function of M3 as well, with the appropriate signs that you see over here. And you will have not only I22 which we already saw here, the moment of inertia about the x2 axis, but also 3, which is essentially the moment of inertia about the x3 axis, the vertical axis. And we will also have what is known as a product of inertia, I23, which instead of x3 squared dA or x2 squared dA has an x2 x3 dA. So you're multiplying both x2 and x3 coordinates and then integrating over the entire cross sectional area. We end up with I23, and that's going to be there as well. For symmetric cross sections, this will vanish, and therefore you will see that there will be no coupling. In other words, your M2 will depend only on U3 double prime and your M3 will depend only on U2 double prime. Only when you have asymmetric cross sections or you are taking along what are known as non-principal directions, because principal directions for the moment of inertia will make sure that you make a rotation such that your I23 goes to 0 in the new coordinate system, then this coupling will not be there. So this coupling happens if and only if you have non-principal directions. And principal directions, again, you have to be careful because there's a principal direction associated with stress, which is not a material property at all. There's a principal direction which is associated with the mass moments of inertia, which could be very different. Principal moment associated with the moment of inertia that we see here, pure geometric property, which could be another third number, etc. So be careful with that. So once you determine the principal directions and take x2 and x3 along that, you don't need to bother about these two terms. We can solve these two problems independently because they'll not be coupled. But once you have non-principal directions, which is many attempts the only way to go, because you might want to use certain specific directions like the direction of the lift and the drag, for example, as the appropriate x2 and x3 to have the aerodynamic inputs more direct and straightforward, etc., in which case you do need to take these couplings into picture. So that kind of covers 3A, which was based on just pure moment, but the bending problem has an additional complication that the moment is caused not only by a pure moment but also the forces that are acting on it, either concentrated forces due to an engine weight or engine thrust or ammunition weight, for example, but also because of the lift distribution or the drag distribution that's going to cause a shear force, right? So the simplest case that you can think of is just a tip load of V which is acting over here, which is on any cross section going to cause a shear stress. But in addition, that V also has a moment arm as we go in deeper inside towards the root, and that will have a non-zero moment. So that will cause, just like in this earlier problem, it will cause a certain bending stress, which is sigma 11, a bending strain, which is epsilon 11, and the bending displacement, which is U3. But your V is going to cause an additional shear stress that is going to be there, which is going to make things rotate. So that's additional rotation that we have to take into consideration. In other words, the cross section over here, as I said in an earlier class, is going to, as this beam curves, because now the load is upwards, this is going to curve this way, and when it curves that way, a cross section which was normal to it will go normally along with it. So in other words, normal section remains normal, which we talked about earlier. So that is Euler-Bernoulli beam theory. So it goes like that. But in addition, because of this transverse shear, there can be a small adjustment over and beyond that, so that now no longer it is perpendicular to the reference curve, but a small change is there, and that is what is your transverse shear strain, and that is the primary effect of this, and which of course has an associated rotation and or displacement with that. So that calculation can be made, and eventually you can show that whereas this stress is linearly varying in x3, and therefore it has a large positive value at one end, one edge of the cross section, and the other edge has the smallest value, and in between it goes from positive to negative all the way passing through 0. Whereas in this case it is opposite. The top and the bottom are having 0 stress because the boundary condition on the top and the bottom have to be obeyed. But of course when you're having a low Reynolds number flow across the airfoil, the boundary condition on the top and the bottom will not be 0, but the actual shear stress or viscous forces that are exerted by the fluid flow over the airfoil, and therefore these two values will not go to 0 but will have some other value. So now in this plot, of course, I'm plotting x3 on the y-axis and I'm plotting tau 13 on the x-axis, which is kind of unusual how it is plotted, but just to be in sync with this, that x3 is upwards here and x3 is upwards here. And here you see it is the mid surface that is having the largest stress. So all the way we have been saying that it's better to put the material out, put the material out, it's better in bending, better in torsion, use thin walled circular tubes, use I sections which are having all the material farther away from the neutral axis. But here we find an opposite case where it's the material in the middle which is much better at resisting the transverse shear. But we still go about putting material farther away because this stress, even though it's a maximum at the center, that maximum value we can show is much smaller compared to the maximum value of this sigma 11. It's not a bothersome stress, but we do need to take into account, because if we don't take that into account, we cannot account for a lot of failures like delamination, etc. So we do need to calculate that. In other words, we don't take it exactly zero, just like the plane stress example as an assumption that we made. We were talking about all the sigma I3, the plane stress assumption says that take it zero, but we know yes, sigma I3 is very small compared to sigma alpha beta, that is sigma 1 1 2 2 and 1 2, but it's not exactly zero in general, and therefore we do need to take that into account. Similarly over here also, but the what is interesting and very different from the other problems, and sometimes kind of non-intuitive also, is that the middle cross sections are much better at taking shear, which is why the sandwich construction that we talked about earlier, the face sheets on the top and the bottom, they take the tension and the compression coming from the bending, but the inner core or an aluminium honeycomb, for example, they take the shear, because that shear is going to be maximum in the center, and these things like foams and honeycomb constructions are really good at handling that kind of shear stress. Okay, so and also there it was linear because it's proportional to x3. Here it will be kind of quadratic, in particular parabolic in shape, and so parabolic shear stress distribution. What we are bothered about from a design perspective is just its maximum value. We know it's going to zero on the top and the bottom because of the boundary conditions. In this case, I am not applying any shear on the top surface, I am not applying any shear on the bottom surface, and because there is no body moments involved, we know that in a plane perpendicular we should have zero stresses as well at the top edge and bottom edge, and therefore this is purely coming from a boundary condition. In between it is allowed to go to a larger value, and that largest value that it can go to is given by that load V, and it's the same at all cross sections, because the shear force diagram, if you draw, it's V constant throughout, and therefore you can see that this is given by 3 by 2 times V by BH. Now if you look at equally distributing this force on that cross section, that cross section has a breadth B and a height H. It's a rectangular cross section. Area is very easy to see. It is BH. So it's just force divided by the area, B by BH. That is the, if it were to be distributed equally, average stress, that is V by BH. But what is happening is the maximum is about 50% more than that, because a factor 3 by 2 is involved, and therefore it is 1.5 times the average shear stress that is there, and which is why designing the interior for shear is so very important. Now we just want to compare this maximum with the maximum value of this, so that what I told you, you can have a feel for that. So now sigma 11 max we try to determine. For to determine sigma 11 max, this is the full expression for sigma 11 max. All that I have to do is to see where these quantities are going to go to make sure that sigma 11 is maximum. I22 doesn't change from point to point in the cross section. It's the one value for the entire cross section. So that remains a constant. The only way sigma 11 increases is by increasing M2 or increasing X3. Where will X3 be maximum in terms of magnitude? Either the topmost edge where it is tension, or the bottommost edge, sorry, in this problem the topmost edge is under compression and the bottommost edge is under tension, because of the way I am applying the force V along the positive X3 direction. So the lift force also is similar to this. So the top is going to have the compression, the bottom is going to have the tension, and where your X3 magnitude goes to the largest is on the top surface and the bottom surface, and where M2 goes to its maximum. M2 is the same for a given cross section, but as you go along the cross section, you will see that the V's moment arm is going to keep increasing. At this end, the bending moment is 0 because the V is acting through that point. So there's moment arm is 0. But here it's the entire length of the beam. So it becomes V times L, and therefore it becomes the largest bending moment is at the root, which is the case in the case of the aircraft as well. Even though you don't have a tip concentrated load, you have a distributed load. Still, in that case also, it is at the root that you will typically have the largest moment, and you will have the largest cross-sectional area also. If the cross-sectional area is changing, which means that you have a tapered beam, then you should make sure you take that I22 also into account, because I22 also is changing along the length. And typically you will see that as M2 increases, I will increase my I22 such that this ratio is either a constant or is within a small variation. So that may not be a big factor in a tapered beam, which is designed appropriately. Only difference will come because of X3 changing. So topmost and bottommost will be the most important things. But in this problem, it's not like that. Here, it's a prismatic beam. So therefore, constant area, shape and size are not changing along the length. So therefore, your I22 is a constant in this example, not in the wing example. And also a helicopter rotor blade also typically it will remain constant for most helicopter rotor designs. And then in that case, you see that I am substituting the largest value of X3, which is h by 2. Of course, the negative will be minus h by 2, which is also of interest because the compressive stress, what is the maximum also I have to look at. But the tensile stress is essentially, sorry, it's the other way around because of the direction in which the load is applied. But essentially, you can see what I'm saying, that the maximum value you can take is h by 2, and the maximum value of the moment is V times L at the root of the beam, and therefore VL times h by 2. And this, for this rectangular cross section, the moment of inertia is given by breadth times height cube divided by 12. Once you substitute that and you make this simplification, you get 6VL by BH squared. Now I can separate out V by BH, which is V divided by BH was the factor that we got here as well. So, and we got a 1.5 times that. Or over here, the factor that we have is if you take the ratio of the maximum normal stress to the, because of bending, to the maximum stress because of the shear, which is the shear stress, you get a factor 4 times L by H. Already 4 makes it 4 times, but what is even more going to make it even bigger is L by H factor, which can be of the order of 10 or even 100 for many airfoils. It's a very thin walled airfoil, it can be as large as 100, but for most typical ones it will be of the order of 10 or more, which means that this is like 40 factors that we are looking at, very large compared to 1. Therefore, many a times for a first cut analysis, you might even ignore the effects of the shear stress and just bother about the bending stress alone, even though you have non-zero shear forces in your actual problem. Okay, so I think this kind of takes care of what we wanted to discuss. Yes, transverse shear is important only for short and stubby beams. In other words, either L should be very small or H should be very large, so that the L by H ratio is not of very large value. In such a case, you would see that the beam, as far as the geometry is concerned, is essentially a shorter beam, and it's stubbier beam, which means much thicker, to the extent that you can't even call it a beam anymore. So because it's becoming, so cross-section area is increasing in size and the length is decreasing, you're moving more towards a 3D body rather than a beam. But as long as L is reasonably large compared to H, you might still model it as a beam, and there's where the problem is, because once you have L by H not very large compared to 1, it's kind of a sin to model it as a beam. You really should not be doing that, and obviously you will reap the consequences if you do that in terms of the large errors that you end up with. So we have another small short homework based on this, which is to derive the ratio of tau max by sigma max, which is what we did over here. Sigma max by tau max we already did for one cross section, which is a rectangular cross section, but instead of rectangular I want you to check out an elliptical cross section, and instead of the kind of free kind of boundary condition that we had over here, you are going to be looking at a simply supported beam, which means one end is hinged, the other end is also hinged but on a roller. So it's freely allowed to move in the horizontal sense. So that's what we call as a simply supported beam, which on many of my future slides in the future classes also will be abbreviating as SS. Beam with uniformly distributed transverse load. So another complication I'm introducing is, instead of just this tip load V that I'm showing over here, I want a uniformly distributed load, which is still simpler than what you're going to have in the airfoil, because the wing typically will have a kind of an elliptical distribution. That is the simplest model, based on the simplest model. Once you bring in other complications and attachments, etc., it's going to be much more complex than that distribution. But we want just a uniform distribution, in other words, a constant force per unit length, which is distributed throughout the length of the beam. And for that case, we want to see what is tau max by sigma max. Once again, you will see that it's going to depend on your L by H factor, and the conclusion, the takeaway will be that short and stubbier beams are the ones where tau max plays a much bigger role, but the factor will not be the same. So you will have different factors associated with it. Then we can compare how different it is from a rectangular to elliptic, and here you have much more complex than elliptic, which is the airfoil cross section. Different airfoil cross sections can behave much more differently, and there you may not even have analytical solutions like what you can do with these standard shapes, rectangle, circle, ellipse, etc. Here you do need to have numerical considerations or a numerical model to handle this kind of a problem. Yeah. So I think with this we complete the 3 examples. So if you have any questions or doubts in terms of this overall structure of 4 variables and 3 equations, combining all 3 equations, and then eventually putting it in a form where there is an input, there is an output. Input or cos is your load, and output is the displacement. In one case it could be a rotation, but we are using displacement in a generalized sense, like we use the word force to refer to moments also in a generalized sense. So because the behavior is very similar, and then the correlating factor will involve always one material property and one geometric property. These might take more complex forms when you go to let's say a composite material and or more complex shapes like airfoil, etc. But essentially this is the form in which it will be, and the designer therefore has 2 levers to play around with. One is the change of the material, the other is the change of the size and shape of the cross section, with both of which we can make a huge difference in terms of how the cause effect relationship is. Okay. Right. Let's move on then. Yeah. For the same example, because we've been saying that in bending the I section is very good example, and these homeworks you can divide amongst yourselves, so as usual, so that not all of you need to do all these problems. So you split and each of you focus on one of the problems, so that then when you present, everybody gets advantage of that, right? So and of course you have 1 week duration to actually wind it up and submit it along with the previous homework, which is not yet done. So this is continuing with the bending problem. Efficient beam cross section we already saw means that you should have a large I, and if it should have a large I, which is integral of x3 squared dA, then you should locate the material farther away, unlike for the shear where you should locate material closer. But shear, as we saw, the maximums are much smaller compared to the maximums of the bending stress and or the other stresses like torsion, etc. All of them are better handled by pushing the material outside, away from the so-called neutral axis as far as bending is concerned. Right, now if you look at a typical shape of an I cross section, you will have thin, 2-3 thin rectangular strips which are joined to each other in this fashion, which is when you get into an I. But the actual way in which this could be constructed, for example in the case of a composite, would be that you make thin layers which is still wet and you can easily bend them. So then you take a layer which is like this and you actually bend it like this, and similarly you take another layer here and which you bend it like this, and then you start stack up on the top. So what I mean is, just show over here. So it's just one layer which you then tend to bend it at right angles at two ends, and then you try to put it over there, and similarly you keep doing this over here. So this is a second layer which you have bent into a C like that, and then you put top layers over here on the bottom. So essentially it is created in this particular way, so that this joint is having a reasonable strength and it doesn't break at these joints between the flange and the web. So this is what we call as the web, as you know, and the top flange and the bottom flange. Okay, but what we are showing here is a simpler example where we are not using composites. Let's say you use just an isotropic material. Once again, geometry is very similar, that it's a wide flange. In other words, the width B that you have is much larger compared to the thicknesses of all the three walls. In general, you could have different thicknesses for the web and the flange. So web thickness is given as TW. T subscript W, and T subscript F is the thickness of the flange. This is a symmetric cross section, therefore the top flange and the bottom flange are the same width and same thickness as well, that is B by TF and B by TF. But you can have an asymmetric cross section as well, which is very common in aerospace applications, and you will see that B by TF can be very different for the top and the bottom, right? Now, so here is a symmetric wide flange I section beam, and here if you are having let's say a bending load, that bending load is taken in this particular manner, which we can very easily prove from the fact that an x3 by I22 factor is involved, which is the amplifying factor for M2 to get into your sigma 11, and when we plot sigma 11 integrated with respect to the thickness over here, you would see that this is the kind of curve that you end up with, because the width over which it is acting is just the thickness in the middle, but the width over which it is acting is much larger in the flange, and because of that factor, that B by TW is so large, therefore the most of the bending loads, which is in the form of axial stresses, tension and compression, are taken by the flange, the top flange and the bottom flange. One takes tension, other takes compression. And the in between, it's hardly taking any bending at all. But when you go to the transverse shear, we know, see, when you had a rectangular cross section, this whole thing was linear. But once you brought in an I section instead of a rectangular cross section, you have piecewise linear. So these slopes are one and the same, but just they are pushed apart. Why? By that factor B by TW. That factor B by TW is what is pushing them apart, but the slope remains the same. Okay, it's piecewise linear with same slope but discrete, because essentially there's a jump where the web joins the flange. Okay, same kind of a thing here. We already saw for rectangular cross section, it is 0 on the top, 0 on the bottom, reaching a maximum in between, and that was 3 by 2 times V by A we saw for the rectangular cross section here. So there, and in between, of course, it's essentially a parabolic distribution. Now here also it's a parabolic distribution, but a piecewise parabolic distribution. Here it is a piecewise linear distribution, it's a piecewise parabolic distribution. In other words, the same things that we discussed with the rectangular cross section are taken here, because these are piecewise rectangular cross sections. This is one rectangle, this is another rectangle, that's a third rectangle. But the way these rectangles are oriented with the larger and shorter edges is different for the web and the flange, which is what is making this difference. And you see, as far as bending is concerned, it's predominantly taken by the top and bottom flange. The web hardly contributes, whereas if you're taking the shear, which is anyway a smaller effect, but relatively speaking, almost the entire thing is taken by the web, and the flanges don't contribute to it at all. Okay, so in other words, all of them play their role. So it's not that the web is a waste. So web is playing a role. It's taking the transverse shear this way, and transverse shear comes not only because of the drag and the lift forces distributions, but also because of the pitching moment, which creates a torque, and that torque, remember, has to be taken by this wing box. So the wing box has to resist that torque, and when that torque is resisted, that's also going to create a shear stress, not only in the top and bottom skin, but also in the webs of the front and rear spars. And that's going to add up to whatever shear distribution we have here, and the total shear distribution is what is of interest to us. So now, based on this, we have again a very short example that you will try out in the as part of your homework. We are going to look at these ratios. Just like here, you see that I am saying that this is taking much more bending load compared to this. This is taking much more shear load at the web compared to the flange. So similar kind of a thing we want to do for instead of let's say a fixed free or a simply supported, etc. Many space applications are where you have structures which are just floating around in space, and typically a free kind of a boundary condition. So when you have something like that, how do you get this ratio of the shear stress? What is maximum in the flange to the what is the maximum in the web? Obviously, it will be a very small number because flange will take very less compared to that. On the other hand, if you take the sigma max and reverse it, this will also be a fairly small number because the flange will take most of the normal stress over here. So we know these are going to be very small numbers, but we want to get a feel for it, and that's what we want to do. And instead of doing it for a I section which is kind of symmetric, we want to do for an unsymmetric section where let's say we don't have this bottom flange at all. We have only the top flange, we have the web. So it's essentially like a T section now instead of an I, and that's what we are looking at over here. And now, as far as the support is concerned, we can think of it as on an elastic foundation. So that elastic foundation is like a spring system, which is a distributed spring, which is essentially giving you, it's a linear spring constant. So it's essentially giving you an equal force depending upon the displacement. Where there is more displacement, there will be more force, reactionary force, which is coming because of that. And for most free problems, this is one way you can handle it by introducing a pseudo elastic foundation, do the derivation, and eventually you can set the spring constants to 0 to get to a free beam. Okay, so that's one way you can do it. And this time, as far as the load is concerned, we don't want just a tip transverse load, but and not even a constant uniformly distributed load, which we took in the previous example. But now we are getting a little more closer to reality in terms of what is used on an aircraft, which is an elliptically distributed transverse load. So in other words, the load is along the span. So this is Y, let us say. So along the span, you have the half span over here, and this is the root where the wing is attached to the fuselage. So you typically will have an elliptic distribution like this. In other words, your lift distribution will be something like this. Closer to the root will be the maximum lift and lift per unit length, that is, and the lift per unit length will become almost 0 to close to the wingtip, because you're going to have vortices which are going to come over here, and therefore the pressure is the same on the top and the bottom. It's the differential pressure which causes the lift, and which is going to be much more closer to the root. Of course, you have a much larger airfoil cross section there as well. So all of that is going to matter, and this is what you have. So under this load, we want to get this. And when we say maximum, it's not just at a cross section where the maximum is, but also along the length. And here it is very clear to see that whether it is the shear force or the bending moment, both of them are going to be highest at the root. So you just focus on the root cross section, you will get all your answers. But within the root cross section, where it goes to maximum, minimum, on a T section beam where there is no bottom flange of the I section, only the top flange and the web are there, that is essentially the complexity of the problem, because now you have only one plane of symmetry, there is no second plane of symmetry, and therefore you have to calculate where you want to take that, find the neutral axis and do all that. So essentially this problem will get you up to speed on the three examples that we discussed, in particular the last third example that we discussed. So is this homework clear? Yeah. So make sure you decide amongst yourself which problem each of you is going to tackle, so that you are kind of focused and everybody benefits when you make a presentation, right? Yeah, we still have a few more minutes. Let's go ahead. Yeah, so now we can kind of combine all these three examples into one single matrix equation. If you look at the first row, okay, first of all, let me introduce these new variables that I've brought up here. So remember the three causes that we started off. The first example was an axial load F1, right? So this is the axial load in a rod problem where we just applied tension on both sides, but we said that the same thing is valid for compression as long as it doesn't buckle, if it's lower than the critical force, right? Then we have two more which are associated with the shear, but we saw that shear makes a very less contribution, the stresses are very less, so for now let's not bother about that. But we considered the second example we considered was a moment, which was a moment which was twisting, it's a torque, and therefore it was twisting the structure. So this is essentially your M1 because it's parallel to the X1 axis once again, right? So that's your torque. Then we considered a bending moment problem where we could have either M2 or M3 or both. And this is more common because you have both a lift distribution and a drag distribution, and therefore it's going to bend in both directions. So unless you have found out the resultant of M2 and M3 and you're applying in some other direction M2 star and therefore taking care of both simultaneously, that's another way of approaching the problem. But these two, both of these are essentially your bending. So it's a bending moment, a torsional moment, which you can also call as torque, and an axial load, all of these, okay? Now these four are going to be related linearly because we have, remember, use geometric linearity and material linearity because your constitutive law is linear, your kinematic equations are linear, you're just defining your strains as gamma 11 equal to dou u1 by dou x1, not taking the quadratic terms. In your matrix relating the sigmas to the strains, gammas, you're taking the matrix of all constants, Young's moduli are all constants, the shear moduli are all constants, the Poisson's ratios are all constants, etc. So therefore, because both of these are linear models, you end up with constants in this particular thing. And this is going to be related to four strains, but now all of them are in the form of one-dimensional strains in the sense that much simpler, depend only on x1. Earlier, all strains gamma 11, gamma 22, gamma 33, 2 gamma 23, 2 gamma 31, 2 gamma 12, the 3 normal and 3 shear strains were all 3D strains. They in general depended on x1, x2 and x3. Now we have reached a case where it's a very, very simple thing where there is an extensional strain gamma 11 bar which depends only on x1. So this is your extensional strain, which is a direct result of your axial load. Okay, and the relation between them is the first row, first column. So the first diagonal element has to be populated because of that. Remember that we derived that expression and we showed that F1 is equal to EA times dou U1 by dou X1, right? So similarly, we had shown our M1 is equal to GJ times dou Phi1 by dou X1, right? And the last thing we showed, of course, was we applied an M2 and we showed that is equal to EI22 into dou squared U3 by dou X1 squared. And if there's a plane of symmetry, then you would have M3 is equal to EI33 dou squared U2 by dou X1 squared, right? So now these two together we did in the third example because they are very similar, just that you're changing the direction of the moment. Whereas this is very different. This moment is a torque and this is a axial force, and these were the three examples that we considered. So example 1, example 2, and both of these put together in example 3. Now all that we are doing is combining these three into a single matrix equation. Now what is it relating? So this dou U1 by dou X1 is essentially a function only of X1, and which is what I'm going to call as your gamma 11 function only of X1. Earlier I was using capital gammas to refer to strains which are functions of X1, X2, X3. Now I have a much simplified version. I'm therefore using a lowercase small gamma in Greek alphabet, and we are taking that as a function only of X1. In a statics problem, dynamics will involve time as well. Similarly, this particular quantity dou Phi1 by dou X1, which is a twist rate, twist per unit length, this is what we are calling as kappa 1 of X1, right? So this is essentially the twisting curvature, if you want to call it, right? So this is extensional strain. The next one will be your twisting curvature, which is also now a function only of X1. Similarly, of course, these will also be functions only of X1, right? These are all one-dimensional stress resultants. We started off as a load, but essentially it could be a bending moment or a torsional moment distribution or an axial force distribution along the entire length because of the actual load that is applied either at the ends and or distributed loads in between. So you can draw shear force diagrams, you can draw bending moment diagrams, etc. to get the distribution of M2, M3 along X1, like for in that elliptical distribution of lift, for example, you're going to do that essentially for determining M2 as a function of X1, etc. So you have axial load, torque, and two bending moments, and that's related to extensional strain, twisting curvature, and the two bending curvatures. So two bending curvatures are kappa 2 of X1 and kappa 3 of X1, right? So let me use a bar to be consistent with that notation. Yeah, so this is what you typically have. So this notation of bar is typically when you're using only one force and three moments. When you use all three forces on all three moments, which is what you have in terms of like a rigid body degree of freedom of 6 degrees of freedom for the cross section, then you will have F2 and F3 also coming in, and in that case instead of barred quantities we'll have just simply only gamma 1, only kappa 1, only kappa 2, only kappa 3, along with gamma 1, 2 and gamma 1, 3 rows inserted in between. So let's not bother about that right now. And what is your kappa 2 and kappa 3? So this is essentially dou squared U3 by dou X1 squared is kappa 2. Look at the flip that is there. The derivative of X3 U3 is kappa 2 because that is the curvature about the 2 direction for a bending moment applied in the 2 direction. Whereas dou squared U2 by dou X1 squared is what you have as kappa 3. Okay. So that's what you see over there, and all our results that we already got, we are just combining them together, and this is possible only because we have the linear model, and therefore principle of superposition is valid. Principle of superposition is you can break up the complicated problem where all of these loads are acting simultaneously, then treat each one of them as separate individual simple problems, get the results, and then combine the results, which is what we have done by assembling them into a matrix over here. And in this simple case, there are no couplings, so therefore all the off diagonal elements are 0, but in reality you will see that some of these elements can become non-zero, especially when you have composites and or non-linear models or asymmetric cross sections. Already we saw an example when we have asymmetric cross sections, a product of inertia can come in, and you can have an EI23 that is coming in these two. So that is the simplest example that you can see, which we already considered in fact. Okay. Now we are considering a symmetric cross section. When you have a symmetric cross section, that I23 will go to 0, and therefore this off diagonal term will also go to 0. Similarly, there can be a coupling between extension and torsion, what is known as the trapeze effect. There can be a coupling between extension and bending. There can be a coupling between the bending and the torsion, etc. So you can in fact design structures to have those couplings, because that might be beneficial in certain applications. So you actually design the shape in an isotropic material, that's all that you can do, or you can design or change both the shape and the layup in the case of a composite in order to achieve that. Even with simple shapes in a composite, you can get many of these couplings which might be desired, or if it's an undesirable coupling, how to reduce it, that can also be done by using appropriate composite layups. So that's where you end up with these terms: the axial stiffness, the torsional stiffness relating M1 to kappa 1, and then your bending stiffness relating the bending moments and the bending curvatures to each other, and the rest are all zeros that you have over here, right? So this is consolidated. So this is the relationship between what this column matrix over here is called is the stress resultant. Why do we call that? Is because you are just integrating the stresses and or the stress multiplied by a moment arm. For example, your F1 will be defined as an integral of sigma 11 over dA. Over the cross section, you are integrating sigma 11, so you are getting essentially a force. That is essentially what you are doing there, which is similarly you can define your M1, M2, M3 along with a moment arm. Apart from just integrating a stress, you will also have a length quantity, and therefore these will differ from that by length. Okay, so that's why these are called as stress resultants, and these are called resultants plural, and these are called as the 1D strains. In other words, these are one-dimensional strains. So in terms of these one-dimensional strains, you have got the stress resultants. So in other words, you no longer need to use these three equations separately. That is, the equilibrium equations, constitutive law, and kinematics separately. You are going to combine all of them together to get these constants of proportionality. And of course, this can, for a tapered beam, EA can be a function of x1, GJ can be a function of x1, EI2 and EI3 can be function of x1 as well, changing along the length of the beam. So that is also possible, okay? And that is very common in aircraft wings. So that is what we have. We just finish this slide and we will go. So EA is, each of these is given a name, just like I gave names for F1, M1, M2, M3, and gamma 11 bar cap and the kappa I bar. Similarly, and here of course I wrote it in a different form over there. Here I am writing it as stress resultant in terms of the curvature. But if I multiply the stress resultant and the curvature, I should end up getting twice the one-dimensional strain energy density, because it's a linear model. Half of the strain squared times the stiffness is what we are getting. So that half factor I've taken to the left hand side, put it here, and U1D refers to energy per unit length of the beam. Usually we refer densities as per unit volume, but here we have integrated over the area of the cross section. We are left with only one dimension, which is x1 dimension. So everything is per unit length, and therefore this is energy per unit length. What energy? Potential energy, in particular strain energy, that is stored within the body in the form of the deformations, the deflections, and therefore the strains. And that strain is once it is released, because it's an elastic material, it will do work, whatever work you did on it to make it get to a different shape and size. Now once you release the loads, that is going to do some work and everything is going to be recovered. So which is what elastic essentially means. So these are two equivalent ways of writing that, because essentially this term and this term, if I multiply, is what I have written on the whiteboard as the stress resultant. Now you're taking the transpose of the strain, multiplying it with the stress resultant, you're going to get a scalar quantity. It's just going to be 1/2 gamma 1 bar squared, 1/2 kappa 1 squared, 1/2 kappa 2 bar squared, 1/2 kappa 3 bar squared, all of them with weighted by their corresponding stiffnesses, and that's going to be your total strain energy. So total strain energy per unit length is going to be composed of extensional strain energy, torsional strain energy, and the two bending strain energies. All of them put together gives you the total strain energy, and therefore these stiffnesses of course are associated with the corresponding deformation. So EA is called extensional stiffness, GJ is called Saint Venant torsional stiffness. The name comes of course from Saint Venant, who is also associated with the Saint Venant principle that we discussed earlier today to avoid boundary problems. Now EI alpha, where alpha takes on the values 2 or 3 as essentially a bending stiffness about the x alpha axis, that is the cross sectional coordinates x2 or x3 respectively. Okay. And E of course, as you know, is the Young's modulus, because we are considering only isotropic materials. So this equation is valid only for, as well as what I wrote on the board, is valid only for isotropic materials. The simplest case that you can have as far as materials are concerned. The shear modulus G and the cross-sectional axis x alpha are principal axis, which is why the I23 term didn't come over here. Otherwise I23 term would have brought in two off-diagonal terms over here. So these are x alpha happen to be the choice, happens to be the principal axis originating at the centroid. For your T section, for example, if you do this, things can get simpler because you will not have that particular coupling in place, and you can deal with it much more easily. So principal axis and originating at the centroid, in other words, those principal axes are intersecting with each other at the centroid of that cross section. It's a uniform cross section, so whether it's center of mass, center of gravity, and or the centroid is one and the same. But when you have different materials, a hybrid kind of a cross section, you have to be very careful in not interchanging these words and using the appropriate terminology of CG, CM or centroid. Okay. So thank you. With this we complete today's class. We'll meet next week. If you have any questions, I'll be happy to answer. Okay. Thank you then.